When you first learn SQL, you practice on a single, isolated data table. But in a real production environment, that simplicity rapidly expands into an interconnected ecosystem of hundreds of tables. Querying one isolated list is fine for learning the basic syntax, but extracting actual business intelligence requires stitching together disconnected systems from across the entire enterprise. To combine these complex datasets effectively, we have to look to mathematical set theory. We are leaving manual spreadsheet manipulation behind. Our objective is to engineer automated, high-performance reporting pipelines directly within the database. Professional database administration requires moving beyond isolated syntax to master these architectural relationships. The SQL join commands you type aren't arbitrary keywords. They are physical representations of Venn diagram intersections and unions. Let's establish two enterprise sets. Table A represents active players, and Table B represents in-app purchasers. Notice the exact center overlap. This intersection returns only the records that perfectly match in both tables. In SQL, this is an inner join. If the marketing department asks for a list of VIPs, specifically active players who actually spend money, you run an inner join to extract that precise segment. Now look at the union, which combines the entirety of both circles. This translates to a full outer join, retrieving everything from both tables, matching what it can, and padding the remaining gaps with blank null values. Finance departments rely on this exact structure to generate a complete ledger of every player who has ever logged in or spent a dime, leaving zero activity undocumented. Visualizing data strictly as sets prevents syntax guesswork. It provides a consistent logical framework for even the most ambiguous business requests. Sometimes the relationships we need to map exist inside a single entity, like an employees table where a worker reports to a manager listed in that same dataset. Here is the code block for a self-join. If you instruct the database engine to join the employees table directly to the employees table, the system will crash from recursive confusion. To execute this safely, we use aliases to trick the engine. By labeling one instance E for the worker and M for the boss, we force the system to treat the single table as two distinct queryable entities. We apply a left join here for a specific structural reason. The CEO has no manager. Without the left join preserving the primary table, the top executive would entirely disappear from your hierarchy report. This diagram illustrates a different architectural pattern. Relative difference. Instead of finding data that matches, we are now looking for what is missing. This technique is called an anti-join. It isolates records in Table A that have absolutely no corresponding data in Table B. SQL lacks a dedicated anti-join keyword, so we construct it in two steps. We attach the data using a left join, and then we strictly filter the results using a where is no clause to capture the void. In practice, this allows us to isolate active players who have never made an in-app purchase, giving the marketing team the exact target audience for a first-time discount code.
Mastering this void is just as critical for proactive business interventions as analyzing the data that already matches. Every query forces the server to physically move data from the hard drive into system RAM to process the logic. An inner join has a lightweight memory footprint because it immediately discards unmatched rows. A full outer join is heavy. The server must hold the entirety of both datasets in active memory to generate all those blank padding spaces. This graph visualizes the computational cost of a severe mistake, joining a 1 million row table to a 500,000 row table on unindexed columns. Without an index to guide the search, the engine checks every possible combination. That creates an n times m time complexity, resulting in trillions of operations and a likely systemic failure. The primary defense against this failure is pre-indexing. Primary and foreign keys act exactly like a textbook's logical table of contents. By joining your tables strictly on these pre-indexed keys, the database skips irrelevant rows. The time complexity drops to a logarithmic scale. This is the unbreakable rule of database physics. Always join on your keys. It turns a 10-minute query into a 10-millisecond execution. Once you have merged and optimized your datasets, the next phase of enterprise architecture is manipulating that data without human intervention. This diagram shows data binning in action. By writing SQL case statements, we automatically evaluate raw numeric purchase amounts and segment them into designated buckets like whale, dolphin, or minnow. Marketing teams rely on these automated buckets to target users instantly, completely removing the need to manually sort data in Excel. However, hard-coding a static number, like a flat $50 average spend threshold, creates a rigid vulnerability. As the economy changes, that hard-coded number becomes obsolete. We solve this rigidity by using subqueries. By embedding a secondary query inside your main query, you force the database engine to dynamically recalculate the current average every time the report runs. Layering case statements and subqueries on top of proper set theory builds a future-proof, self-updating reporting engine. Entry-level workflows typically involve pulling raw database results and exporting them into external spreadsheet software to calculate totals. We can eliminate that step entirely using a native aggregation command, with rollup, appended directly to a group by clause. This command forces the database engine itself to calculate exact subtotals and grand totals across multiple dimensions simultaneously. It removes the requirement to build external pivot tables or license third-party analysis tools just to generate basic financial ledgers. We moved from simple, isolated queries through the mathematical logic of sets and the physics of memory indexing, all the way to dynamic automation. Engineering business intelligence systems natively in SQL automates the data lifecycle, allowing developers to design systems that update and summarize themselves.